Our next topic is related to IVRT duration and linearity. Um, so we already heard from Sam that although a minimum linearity or R-square value of 0.9 across the IVRT duration was recommended historically, but actually the linearity of the release profile across the duration of the IVRT is expected to be more or equal than 0.97. And reality is whenever the R square value is less than 0.97, there is something wrong with the IVRT profile and IVRT method. And as Sam mentioned, R square may be a generous criteria. So it's prudent to making sure that you have the linearity of more than equal than 0.97. And I have examples in the next slide, which I will get to that in a minute. But I would like to also talk a little bit about the duration of the IVRT, which is the next bullet point. I think that has been also covered earlier in the morning. So as it's recommended in the USP chapter 1724, conventionally, a duration of 4 to 6 hours is recommended for the IVRT. And we heard from Kailas in examples where we may need to run longer IVRTs for some of the products like slow releasing ointment. But it's really unconventional to see IVRT that are done less than 4 hours. And usually if there is a reason like higher dose depletion or having inadequate solubility or getting to the plateau in your IVRT curve, these are something that can be resolved by optimizing your IVRT method rather than shortening your IVRT study. But if, let's say, someone submits a well-validated IVRT that is done with less than 4 hours, what justification is needed to support that? Maybe our FDA members can chime in. Or anyone else from the panel.
I just want to make a comment there. I don't have a straightforward answer of what justification, but it really depends. This is your product. You have to, as Kailash showed, the efforts. What we are trying to look as a reviewer, or as a review discipline is we just want to make sure that all efforts are made to develop the right method. And on a specific situation, yes, maybe there is specific consideration for a particular drug product, but majority of the time we don't see any concern, having a 4 to 6 hour study. And some of the cases, even you have to go for a higher than that one. But I think the short answer is, I think majority of the time, I think 4 to 6 hours is sufficient for the IVRT studies.
So if one observe a high release in the first 1 or 2 hours, do you recommend them to redevelop their IVRT method and not submit a 2-hour IVRT study?
It depends how much effort was made to develop that method. So is it something that you have a receptor solution where everything is just, let's say you are using an immersion cell using, for example, I mean, this is the worst case scenario. This wasn't actual scenario, but you are using 100% on DMS. So using an immersion cell, you have a first time point, which is 30-minute, dose depleted 60%. I mean, I think you better, just like, work on your selection of apparatus, receptor solution, or membrane to fix that issue rather than just cutting down on the number of hours for IVRT study.
Okay, thank you.
Can I just quickly go back to the previous bullet, but you say ability of the linear steady state, and if you just calculate your data and say you have 0.97 point and you meet everything and you think, oh great, I got great linearity, but I would highly recommend sometimes visual looking at the data is so much more important that what Sam was showing you, that there's a little curvature. You'll get a 0.97, but you have a curvature. That you need to know that when you're developing your method, that you need to look at your data in graphical form sometimes to see what kind of a shape of release profile you're getting. And I think that that can't be, there is no substitute for that.
You're exactly right. And I will show that in the next slide with some of the examples. So the next topic here is the dose depletion and loss of steady state. We heard a few times today that while the steady state release kinetics is assumed when dose depletion is less than 30%, it's not really a cutoff criteria. And there are a lot of cases where we observe higher dose depletion, but the IVRT profile is sufficiently linear and acceptable. So I think Sam also mentioned that if you are observing dose depletion of, let's say, 40%, it doesn't mean that you should shorten the duration of the IVRT just because your last time point release amount passed or exceed the 30%.
I think can I say something there? I think I saw in the chat where somebody asked, what would that be the cutoff for dose depletion in that case? You know, we, like you said, historically we looked at 30%, and now we are saying that, you know, it doesn't necessarily mean that your method is not sensitive enough or specific enough. So as a reviewer, what am I looking at? So what would be the cutoff that I will kind of just based my assessment on?
So I think you can say with high confidence, like the absolute cutoff, if someone goes above 100%, there's a problem with the test. Other than that, I'm not sure that it's a clear, cutoff. The EMA guideline, they actually encourage that they want to see people go up to 70% dosage form release. So I think the way we have to think about it is, very much to look at the data. There was even a comment in the chat about these, what happens if you see 80 to 90% release in the first hour. And we've seen situations like that where the way that the method was developed, you get this huge burst release right in the beginning. It's right in there convoluted with non-steady state, you blow it all out. And then from that point forward, you can't really discriminate anything. So the interpretation is not, in my opinion, that that's a highly discriminating area, and that's a justification for going to 1 hour now, and it didn't matter that you went to 90% dose depletion. I think you really want to. It's a very good guideline, and it works most of the time to go with the general recommendations of the way that the method is developed, the general timeframes that the method is developed. For most dosage forms, it works really well. You're going to end up with dosage form release rates, anywhere in the range of 20 to 80%. And I don't think that there is a review criterion for saying, I'm seeing a certain percentage here, and I'm inherently concerned. I think it's more, as a reviewer, I would want to be aware of what the dose depletion was for other effects that I'm seeing. And it might help me to interpret some problematic things that I'm seeing in the way that the method was developed, or more importantly, in the way that it was validated, where I can now interpret, I think I see what's happening here, because that's fine, but dose depletion is pretty high, so that I'm having trouble. I think we may no longer be at steady state kinetics here, for example. I think that's more where, as a reviewer, it's helpful to look at the dose depletion numbers.
Right. That's why we encouraged our applicants to provide all the details to the agency. That way you can reconstruct how they perform their method, and you can, assess all areas of the method development and validation.
What about the low end? Sometimes the problem from the formulation, heterolytic acid formulation, 5% or maximum 10% you can release and stop in releasing. But those 5%, 10% is very discriminating. Would we accept those low release?
So I've seen, you had shown some data on that, and I'm not sure how to interpret those early curves. And again, the idea that that's discriminating more discriminating than the later part when you have no release. So I understand the time when you have no release, you can't discriminate one formulation from the other because neither is releasing in that time period. So I appreciate you're looking at the earlier time when at least they're both releasing and you can tell that there's a difference in release. But that, early release, which is a very low percentage of the release, then stalls. So what is that burst release in the beginning? I think it's very difficult to interpret what that is and what that's telling us about the microstructure of the dosage form as opposed to kind of interfacial boundary effects. And because of that, it's, we're not sure that we can, at least I'm not sure that I can interpret that as having mitigated the risk of that failure mode for the product change or for bioequivalence, that failure mode that there's some internal structural difference that's going to manifest as a performance difference clinically. It's hard to make that connection when you're just looking at that early data. I don't have an answer, though, as far as the petrolatum-based ointments. I do think that what Kalis was recommending, which is, perhaps look at longer durations because diffusion through these petrolatum ointments is slow. And so, I think that's a very interesting area of investigation there.
One more thing, Sam. So is it possible to maybe, since they are revising the USP chapter, is it, there's a way to extend the time for such products? Like extend more than 6 hours in that case?
It certainly could, but I think it'd be based on evidence. So before we revise the chapter to go, well, let's try this. Most of the things that are in there are well-established, compendial methods because there's a lot of evidence to back them up. There's a lot of experience to back them up for the most part. And so while I think that this is it's a scientifically promising way to look at it. I myself have not seen a lot of that data. I think, Kellis, you'd be in a better position to speak to that.
Yeah, so I think USP chapter says typical. So these are typical 4 to 6 hours is for a typical semi-solid dosage form. So if you have something that's atypical, such as hydrophobic ointment or suspension or something, then it's a case by case, and then you would accept. You have to look at the scientific aspect of it. You have to look at the due diligence that was done by the sponsor and see what effort went into developing or trying to develop a method. And if they needed to have longer than periods, then there is nothing wrong in having a long duration. So if we say that in USP more, then I think it opens up a very different can of worms, I think. So we really need to stay typical. And that's why we say typical. That doesn't mean all of them have to be 4 to 6 hours.
Thank you. We got a question. Sorry, go ahead.
I just wanted to, I think it's a really important point that Josephine and Kelly that you've just raised here about, looking at it as a scientist, that as reviewers, we're a highly trained, PhDs looking at this. We're, excellent scientists. Well, we got to, put our science and make our scientific judgment really work for us here. When we have either a guideline or the USP, I think that shouldn't become, although it is an excellent resource that allows us to treat all applicants in a consistent manner. I get that. I think we also have to kind of really think through what is the specific concern in an individual application that you're looking at. And when you can identify those scientific concerns, and I know this is what we all do as reviewers as much as possible to really identify that scientific concern specifically, and then try to help the applicant understand, what the concern is and how to address it. The point being that a lot of those are typical situations, but we make judgment calls based upon our scientific insights.
Okay, we received a question that I think we need to address that, and then we can move on to the next slide. So one of the audience asked if we have high dose depletion, are we still at the pseudo-infinite dose?
think that's sort of a philosophical question. And it's a good philosophical question. I don't know the answer to it. I'll tell you, practically speaking, which I think is really more helpful here, because we live in the real world. It doesn't matter whether it's theoretically a pseudo-infinite dose. It has been a sufficient dose, and I think this is what I talked about in my presentation. The whole concept there is not to truly approximate infinity, but to have a substantial enough dose that the risk that you're going to have your dosage form fall into a non-steady state release has been mitigated, and that's a great starting point. Then you just have to kind of look at the data and adapt from there.
Okay, thank you.
Perhaps others on the panel have a different perspective.
Actually, I can add a word. Actually, Higuchi, when you propose, the importance was the initial concentration should be the excess. And nothing is mentioned after release, it should be the still infinite mode. But initially, its initial concentration should be the excess of drug.
Okay, thank you. Would you move to the next slide, please?
This point or the next slide, actually?
Next slide. Thank you.
Just this one, or?
You can select all of, okay.
The bottom ones too?
I can start with this. So these are the examples that I mentioned. So on the left graph, you see an IVRT profile, a release profile, and it actually has an R-square value of 0.98, which seems to be acceptable. However, if you pay attention to the first data point, which was taken at 30 minutes, the release rate in the first interval, it looks to be different than the remaining IVRT duration. And in the graph on the right, we have excluded that first time point, and our release rate has changed and our linearity has improved to 0.99. So if in cases like this, it shows that the first time point was not taken, was not showing the steady state release, and we actually have the steady state release starting from 1 hour. But again, the R square was still 0.9, so it shows that maybe R square is not a very sensitive criteria. If you can go to the next one, Sam. And the second example is where our last time point is having a different release, and the profile is getting to plateau when it comes to the last data point. And if we calculate the release rate using this data, we got a value of 2.8 for the slope, but if we calculate the release rate of the profile, excluding that data, we get to a value of 244, which is significantly different. And also our linearity has been improved. So if even with a profile on the left side with a linearity of 0.97, the last data point is not acceptable to include it as part of your release rate calculation. And even if this is if this is observed at the earlier time, like let's say at 3 hours or 4 hours, maybe you need to look at the solubility of the drug in the receptor solution and dose depletion, and maybe optimize your IVRT method. If this is observed at the 6 hours and you have sufficient samples and covering like you have 4 hours duration of steady state, and maybe you can just exclude that and then calculate the release profile without that.
Yeah, I think these are great demonstrations, and I think it's fantastic, Tanaz, that you put these together. This is often called bottom end lag or top end drop off. It can happen for a variety of reasons. This may be solubility limited, and maybe that the dose depletion has reached a point that steady state kinetics are starting to fall apart. But whatever it is, this is the point that I think Kellis was also making, that not only is 0.9 exceptionally generous and things even more curved than this were being left in, but even if we start saying, okay, look closer to 0.97 and try to be above that, even then, Kellis was saying, use your eyes, use your judgment. If something looks like this, adjust it. Because as Tanaz said, it can really have an impact on understanding what that steady state release actually is and really try to optimize it. And in most cases, you should be able to. One other thing I wanted to highlight, because I'd seen in the chat that there was a little bit of confusion, because we've talked about 0.97, we've also talked about 0.95, we've talked about 0.90. So I think based upon some of the responses in that chat, people generally get that 0.90 has been a generous kind of just a kind of a blunt guideline, and that the higher the R-squared, the better. You typically want to look at 0.97 or better. And the point is we don't want to be too restrictive here, right? But a guideline. So where's the 0.95 come in? I want to clarify this. 0.97 is a recommended R-squared value when you're looking at 1, 2, 3, 4, 5, 6. When you're looking at the time points of release from an individual diffusion cell, or a set of diffusion cells, this is the one that should have 0.97. The 0.95 has nothing to do with this. That is when you've got your 50% strength, your 100% strength, and your 150% strength, and you're looking for the proportionality of release across that. That's the 0.95 plot that we're talking about, because we expect that to have, maybe non-ideal proportionality. So that's why we're not looking for 0.97 there, even 0.95. So that's the distinction between, going forward, the recommendations for trying to stay above 0.97. But even then, make it, optimize it. But the 0.95 is completely separate.